Hey guys, today we're going to be looking at proving and using the angle sum and angle difference identities. Now I've already gotten started by looking at a unit circle with two angles, a large angle A and a smaller angle B. Okay, this creates points along this unit circle, which is P and Q, which have coordinates of cos A sine A for P and for Q cos B sine B, due to our definition of cos and sine that we've gone through for the unit circle. Now, we're using this as a basis for our proof to show that cos of A take B is equal to something which I'll get to in a moment. Alright, so that would be the difference in our angles. So starting with the distance of PQ, I'm going to find this in two different ways. The first way I have done is using my distance formula, okay? Using the change in x, cos A take cos B squared, plus the change in y, which is sine A take sine B squared, is equal to, and the square root, is equal to PQ. Now, if you were to expand that, which I've done here, and simplify, remembering that cos squared A and sine squared A added together will equal 1 from our Pythagorean identity, and same with cos squared B and sine squared B. They will both create 1s, and we have -2 taken as a common factor from the rest, leaving just cos A cos B add sine A sine B. Alright, now if we were to take a look at using our cosine formula for non-right angle triangles, we have A squared, or let's say C squared, is equal to A squared plus B squared. Take 2AB cos of C being the interior angle in here, which is A take B, because we've got to have what's remaining inside here. Take the square root and simplify, and we've got something that looks very similar to what we had before, which I've labeled 1 over here. Okay, if we compare 1 and 2, we can see that this part back here is the only difference between the two. Try that again. And this helps us to show that cos of, I'll move this lower down actually, cos of A take B, so the difference in two angles is the same as cos of A cos B add sine A sine B. Now, just going to scroll up for a second and start our proof for the sum of two angles. So, we're looking at the sum of two angles inside the cos function. And what I'm going to do is make A plus B look a lot like something that we already know, A take B, which we just showed. Now, if we expand cos of A take negative B, we're going to get cos of A cos of negative B plus sine of A sine of negative B. Now, using the identities that I've put up here in the top right that we should remember from previous content, I can simplify this again. So, cos of negative B is just cos of B. So this is cos A, cos B, and sine negative B is negative sine B. So that's going to make our plus a minus, and we're going to get sine A, sine B. So we have our first sum and difference identity for cos, which is that cos plus or minus B is going to be cos of A, cos of B. And now, notice how our sign actually changes when we do this. Alright, so instead of doing plus and minus like we've normally done before, we're going to do minus plus sine A, sine B. All this is saying is that when this is plus, this is minus, and when this is minus, this is plus. Alright, so continuing on, we just need to quickly establish that cos of 90 degrees taken angle is the same as sine of that angle, and the other way around, we have sine of 90, or pi on 2 radians, taken angle is equal to cos of that angle. Okay, and we've quickly established that using our, meant to be a plus there, quickly using our angle and sum formulas that we use for cos. So when we expand a difference in our angles, we get cos of A, cos of B, add sine of A, sine of B, cos of 90 degrees is 0, sine of 90 degrees is 1, so we get that, and then we can flip it by letting theta equal to pi on 2 take sigma, or sigma is equal to pi on 2 take theta, and then we can substitute and get our other formula. Now, taking a look at the difference formula for sine, we can use what we've just shown, that it is now cos of 90 take the angle we just had. Cos of, so I have an angle is equal to cos of 90 take that angle. So there's our angle, there's our angle, and we're taking it away from 90 degrees, change the function. Alright, I'm just going to expand the multiplying by negative into that bracket, and we get 90 take A at B. And I'm going to use 90 take A as one angle and plus B as the other, and use our sum formula for cos and expand it as cos of our first angle, cos of our second angle, take sine of our first angle, sine of our second angle. Alright, and then we can get cos of 90 take an angle is sine of that angle, and sine of 90 take an angle is cos of that angle. And so we have established the difference in angles for the sine function. Okay, if we were to replace b with negative b, sine of a take negative b, we're going to get the same thing. Sine of a cos of negative b take cos of a sine of negative b, and because cos of a negative angle is just cos, like we were using just before, get cos of b, and sine negative angle is negative sine of that angle. I'll just quickly write that over here so you see what I'm saying. We've got sine of negative an angle is equal to negative the sine of that angle, so that makes that minus a plus, and what we had before, cos A sine B. So we've got our second of the sum and difference formulas summarized as so. Sine of A plus or minus B is equal to sine A cos B plus or minus. Notice that when we had a take here, we had a take here, so we don't need to flip it like we did previously. Alright. Cos A sine of B. Alright. Now we're going to move on to tan. So I've kind of skipped ahead a little in terms of the writing. So I'm just going to explain what I've done to establish the tan sum and difference formula that we have here. Okay, we've got a summary of our sine and cos sum and difference angle identities here. Alright, and remembering that tan is sine on cos helps us to get to here. So tan of A plus or minus B is the same as sine A plus or minus B over cos A plus or minus B. Alright, just from our definition of tan, which is sine on cos. Now, using what we already established earlier, our difference formula for sum and difference formula for sine goes on top. Alright, so I've replaced sine A plus or minus B by sine A cos B plus or minus cos A sine B, and did the same thing for cos's sum and difference rule. So, the tricky part about this proof is that 1 on cos A, if we multiply by this kind of odd thing over here, it helps us to really simplify everything. So we can't change anything, so we have to multiply both the top and the bottom by 1 on cos A cos B. Alright, and it starts to look a little bit messy here. Okay, sine A, we have to multiply everything on the top by cos A, or 1 on cos A cos B. So they go to the bottom line of each term. And now, cos B over cos B, they're both going to cancel. But sine A on cos A becomes tan A. Plus and minus, same thing. Same thing with cos A and cos A. They're going to cancel, leaving sin B on cos B, which is tan of B. Over cos A cos B over cos A cos B becomes 1, because they're the same thing, top and bottom. Minus plus, so that one's flipped from our original. Sin A cos A becomes tan A, sin B. Just made a mistake there. I need to make that cos B. Sin B on cos B becomes tan of B. Alright, so I'll quickly summarize all of our formulas which are on the page here. Give us a sec. So, there's our summary for the sum and angles of sum and difference for sine, cos, and tan. So, let's do a quick example of how to use this. Alright, let's say we wanted to find the exact value of sin of 15 degrees. Now, using our difference formula that we have above, we can think of 15 degrees as sin of 45, take 30. 45 take 30, still 15. So we haven't changed anything, we've just changed the way it looks. Now, using our difference formula above, we can go sine of 45, cos of 30. Alright, my sign here doesn't change, so minus minus. We've got cos of 45, sine of 30. And the reason I chose 45 and 30 is because we know the exact values for these two angles in particular for sine and cos. Alright, sine of 45 is 1 on root 2. Cos of 30 is, might make a mistake here, but pretty sure it's root 3 on 2. Take 1 on root 2. And sine of 30 should be a half. Alright. Let's multiply by root 2 on 2. Root 2 on root 2 to get rid of this third denominator that we've got. So multiply both terms by root 2 on 2 and we get that 3 look a little bit better. Okay, we get hold up a second. I didn't bother to multiply them, or multiply the denominators. Alright. It's supposed to be a half to 1 root 2. So root 2 on 2 becomes root 2 on 4. And we should get root 6 take root 2 on 4. I'm a little bit worried about that, but I might just check on my calculator and take a look. So that is fine, but I probably could have done things differently. Using the root 2 out here, I could have done something along the lines of root 3 on 4, take root 2 on 4, and then taking root 2 out as a common factor to get root 3, take 1, all on 4. Both are fine. Alright, let's do one more example and call it a day. Alright, if A and B are acute angles and cos A is equal to 5 on 13 and sine B is 24 on 25, we need to try and find an exact value for sine of A and B. Now, to begin with, let's think about cos A is equal to 5 on 13 and the fact that we have acute angles. Acute meaning that we've got less than 90 degrees, which means all our values are going to be positive. If for some reason it does mention that we're obtuse, you got to think about the fact that we are going to be kind of in the second quadrant area where only sine is going to be positive, but cos and tan are negative. Alright, because we don't need to worry about that. We can use a little right angle triangle, and we know that adjacent over hypotenuse is what cos is, and cos is opposite over hypotenuse. Now, if we were to quickly use some Pythagoras, we could find that that is 12 and that is 7. Now, that's going to help us use or find sine of A, tan of A, and also cos of B and tan of B if we needed them, which we'll come back to in a second. To remember that we can expand this. Sine of the sum of two angles is sine of A cos of B add sine of B cos of A. Now, we know what cos A and sine B are. Not quite sure what sine A is, but we do know that we've got an angle A, and we know that sine is opposite of hypotenuse, so I could say that this is 12 over 13. Cos B, we've got a similar situation. We need to use adjacent over hypotenuse, so we should get 7 on 25. That's sine of B, 24 on 25. Cos of A, 5 on 13 from our original question. And because we want to find an exact value, we don't want to simplify, or we just want to get the simplest fraction, not a decimal. We're going to probably chuck this in the calculator. It would be the easiest one, but if you needed to do it by hand, you're looking for a common denominator for both of these. Alright, 13 times 25 should be a common denominator for both of them, and then at the top. But I'm just going to skip ahead a little bit and tell you that it is 204 over 325. Okay, so using our sum formula and using right angle triangles. One last thing, just a little tip to help you remember at least the sine and cos formulas without going back to them constantly. Okay, sine here, notice that the function changes from sine to cos as we're multiplying those two. whereas cos doesn't. It's cos, sine. Sine is sine cos, cos sine. Alright. But for cos, the sign changes. So if it's a positive on the left, or when you're adding the two angles, it becomes a negative. But with sine, it doesn't change. So if you're adding the two angles, you're adding everything here. So if you know that the sign is going to change, the multiplying two functions won't. You'll get cos, sine. If you remember that the sign will change, or won't change for sine, but the functions, when you're multiplying them, do sine cos, sine. If that makes any sense, just give it a shot. We'll see how it goes. Thanks.